We are talking about function inverses. We want to explore inverses of functions and find and verify inverses of nonlinear functions. So we're going to go through a couple examples, and each pair of functions are inverses of each other. You can use a graphing calculator to graph function f and g in the same viewing window, and then let's see what we notice. So if you want, you can graph these functions. F of x is 4x plus 3, and g of x equals x minus 3 over 4. So we have the two graphs function. We have function f right here, and we have function g. And it looks like they just intersect, but they actually are, if they are inverses of each other, they are reflected over the line y equals x. And so what happens there when they reflect over y equals x is the x and y switch for each graph. So here we can see that we have point 0, 3, and over here we have 3, 0. So when they reflect over the xy axis, the points just switch, and obviously they have the intersection here at -1, -1. So the points switch there also, but they're the same. Here we have another graph, example B. We have f of x equals x cubed plus 1, and we have g of x equals the cube root of x minus 1. And we can see again, both of these graphs, they reflect over the line y equals x. So -1, 0 is right here, becomes 0, -1 on the other graph. And 0, 1 becomes 0, 1 on function g. And that pattern will continue. These are just a couple that I picked out to examine. Here we go with example C. F of x equals the square root of x minus 3, and g of x equals x squared plus 3. And for this one, in order for these to be functions, we have to restrict the domain where x is greater than or equal to 0. So that just means that x is positive. Because if we didn't restrict the domain here, then our function down here at the bottom would have this bottom tail and would not be a function anymore. So here's f of x. So here's a function f. We have the point 4, 1, and then on point g we have the point 1, 4. And then here's our last example. We have example D. We have function f and function g. And I didn't write down the coordinates for these points, but we can see that they still are reflecting over the line y equals x because that's where they are intersecting there. Inverses of linear functions are always functions, but there are functions whose inverses are not functions. So as we can see here, if we were gonna test to see if something is a function, we can remember that we use the vertical line test. And the vertical line test says if I draw a vertical line and it only crosses once, then that is a function. So we know that a parabola is a function. However, right here, this one is not a function because we have 2 points where our vertical line crosses the same graph, so that one's not a function. The thing that we notice about this one is it has an even root. So whenever we have an even root, if we want to see if the inverse is going to be a function, we need to make sure that we have a restriction on the domain for the only positive numbers. Over here, we have a cube root function, and we have g of x is the cube root of x. And this one does pass the vertical line test for both functions, so they are inverses and they are functions. One way that you can test to see if your inverse will be a function or not is you can use a horizontal test. So this is the original function, f of f. We haven't taken the inverse of it yet. You can try the horizontal test. So if you take the original function and draw a horizontal line and it only crosses once at all the spots, then it will be, the inverse will be a function as well. As you can see here, the parabola, the inverse is not going to be a function unless we restrict the domain somehow.